Can you hear that? That's a standing wave. Standing waves have been a well-known physics phenomenon, and our group decided to look further into its importance and the nature in which it serves in the real world. In this project, we have demonstrated the relationship between tension, wave speed, wavelength, linear density, and frequency utilizing a miniature guitar. So first, standing waves occur when a wave is confined between two boundaries, located here at these spots. This is also known as the superposition of two traveling waves moving in opposite directions.
Points that never move are called nodes and create zero displacement, while antinodes are the part of the standing wave, where the particles in the medium oscillate with the maximum displacement. Nodes are placed at half the wavelength apart, and 2 times the distance between the successive nodes creates the full wavelength.
This experiment, we use the INS Tuner app to find the frequencies of our mediums and rubber bands. The strings on a guitar have different frequencies because of their different linear densities. Thus, high-pitched strings are skinnier and low-pitched strings are fatter.
Due to the varying linear densities, we were able to retrieve frequencies. This helped us understand different wave speeds and their direct relation to the change in frequency, which helped us understand the speed of the wave is affected by tension. Our goal was to find the tension of each string based on a specific frequency presented by the varying linear densities of the medium.
So for our calculations for string 1, our skinny string, our known values are our length, our mass, our linear density, and our frequency that we found using its tuning app. We will utilize the 3 equations to find the tension. Equation 1, we will find our wavelength utilizing the length of the median and our number of nodes that we observed. Our number of nodes was 1, giving us 0.38 meters for our wavelength. Our wavelength is then plugged into this formula to find our wave speed based upon our frequency found from the tuning app. Our wave speed is calculated out to be 70.3 meters per second. This value can then be plugged into our tension equation, where we utilize our calculated linear density to find that the tension on the skinny string is 1.04 newtons.
So these will be the calculations for string 2 with our found length, mass, linear density, and our frequency found using the tuner app. Starting with equation 1, we are looking for wavelength using the length and the number of nodes. So with 1 node, we get 0.428 meters for our wavelength. Then equation 2, we use our frequency and our wavelength, and we get the wave speed to be 49.88 meters per second. Then plugging that into equation 3 to find the tension, we get 2.88 newtons.
All right, as you can see here, our skinny string tension ended up being 1.04 newtons, and our fat string tension ended up being 2.88 newtons. So the possible issues with these tensions were that the tuner app was not properly measuring frequency of the wave created by picking the string. It could have also been improperly measuring the lengths of the medium. And then it also could have been, because the medium's volume was so small, it was considered negligible in the calculation.